This video is on Avogadro's law and then a discussion in gas stoichiometry. So up to this point, we've been through the three or four gas laws. I've lost track. We talked about Boyle's law, we talked about Charles' law, Gay-Lussac's law, and the combined gas law. Okay, so it was four. And we've been looking at the relationships between pressure, volume, and temperature. Some of those relationships, deal with two variables, and some deal with more than two, like the combined gas law deals with temperature, volume, and pressure. So Avogadro's law is a little bit different. Now, this is the same Avogadro that you're probably thinking of, our mole scientist, okay? And so Avogadro's law is a little bit different, and this law says that equal volumes of gas at the same temperature and pressure contain equal numbers of molecules. Well, if they contain equal numbers of molecules, they also contain equal moles. Okay, and so this is kind of where we tie, moles back to Avogadro, that there is this additional gas law. It really doesn't have a formula like our other ones, but it says that if I have equivalent volumes of gases at the same temperature and pressure, then those samples of gas contain the same number of molecules and the same number of moles. So to try to put this in perspective, and this is like a famous example that I always use, and I always draw some balloons, okay? So hopefully you have enough room on your paper. My balloons aren't great here. Okay. And so we're going to say that I'm just going to make up some gases here. Oops. Okay, and let me list a couple of questions here. Let's do this. Okay. Now, I need to specify that these 5 balloons have equal volumes, equal temperatures, and equal pressures. So I can make up data and say something like these 5 balloons are all 2 liters, the temperature is 25 degrees Celsius, and the pressure is 1 atm. Okay. However, that being said, that those 5 balloons all have equivalent volume, temperatures, and pressure. So because that's the case, we can use Avogadro's law here and talk about the fact that because V, T, and P are equal, then the number of molecules are equal, and so are the moles. Okay, so let's attempt to answer these questions, okay? My 4 questions. Which balloon's the heaviest? Which balloon has the smallest number of moles? Which balloon has the largest number of atoms? And which balloon is the least dense? So these are fantastic questions. I'll go out of order just for a second because B, hopefully, just from what we've said, B should jump out at you because we just said if V, T, and P are equal, then moles are equal, okay? So when B says who has the smallest number of moles, it's a trick question. They're all equal. Okay? So we also know molecules are equal, but notice my other 3 questions don't deal with molecules. So let's do question A. Which balloon is the heaviest? Okay, well, that's mass. And so what we now know is that all 5 balloons contain equal moles. So what's going to be dependent upon which balloon is heaviest is the molar mass of each gas, right? And so looking at this, hopefully you don't have to do an in-depth calculation because I think pretty clearly you can see that while all 5 balloons contain the same moles, SF6 is by far the most massive molecule here in terms of molar mass, and so equal moles but having a heavier molar mass is going to make SF6 balloon the heaviest. If I asked you which balloon was the lightest, right, a quick glance at those 5 balloons should allow you to say that H2 is the lightest because it's the smallest molar mass. Okay, so C, which balloon has the largest number of atoms? Well, so what is atoms related to? Atoms are related to molecules. Now, so all 5 balloons have equal molecules, okay? But that's not what this question's asking. This question's asking about atoms. And this is where we have to think about, in one molecule, how many atoms are there? Well, in O2, there are 2 atoms, right? 2 oxygens. In CO2, there are 3 atoms for every molecule. In H2, there are 2 atoms. In Ne, there's only 1. And in SF6, there are 7. Right? So which balloon has the largest number of atoms? Well, they all have equal molecules, but SF6 has more atoms per molecule, so my answer is going to be SF6 has the most atoms. And then, which balloon is the least dense? Now, density is mass over volume, okay? So we step back and think about this. I know my volumes are equal. So if I was going to do a density calculation for all 5 of these balloons, my volume, whatever it was, the denominator of this fraction would be the same number, right? If it was 2 liters, it'd be 2 liters for every balloon. So the density of these balloons really only depends on the mass. And so who's going to be the least dense? Well, the one with the smallest mass number, right? Or molar mass, I guess. And who has the smallest molar mass? Most definitely H2. So I wouldn't be surprised if you see a question like that again with these balloons. It's probably the best way to gauge the understanding of gas stoichiometry. Of Avogadro's law. I got excited and thought I was going on. Probably the best way to gauge how equal pressures, temperatures, and volumes can affect moles. All right, so how does this play into gas stoichiometry? Well, it's kind of nice. So gas stoichiometry uses Avogadro's law. So if we have a situation where my temperature and my pressure are constant during a reaction, okay, then we can use volumes like moles to solve stoich problems. And so what that means for us and my way of teaching is we can use volume in liters to write sequences. So up until this point in time, I've only allowed you to write a sequence with moles, right? We call it mole sequences. But if we know that the temperature and the pressure are constant throughout a reaction, then according to Avogadro's law, I can use volumes just like moles. And so this is what we mean by that. So we have a problem that says propane, C3H8, is a gas that is sometimes used as a fuel for cooking and heating. So A, what will be the volume in liters of oxygen required for the complete combustion of 0.35 liters of propane? So, and I should have put this on part A. Assume all volume measurements are made at the same temperature and pressure. So the first thing I have to do, of course, is write a reaction. They tell me this is propane. They tell me it's combustion, so this shouldn't be a problem. So I know I have my hydrocarbon reacting with oxygen, creating CO2 and H2O. Remember, all combustion reactions produce carbon dioxide and water. So I have to balance this. So 3 carbons, 4 hydrogens, and then let's see, 8 oxygens, sorry, and then 4 O's and 6 O's, so that's 10, so I need a 5 here. Okay, so how can I do this? Well, this is really nice. So if I know that I have 0.35 liters of propane, I can just write a sequence with this number. And so, it's been a while since we've done this, but from 1 up to 5, right, I have to multiply 0.35 times 5. And I get 1.75 liters. And that, in fact, is my answer. That was it. That's all I had to do. And I'm allowed to do this only because Avogadro's law makes it possible for me to substitute in these volumes into a reaction because I know that the temperature and the pressure are staying constant. If I don't know that, I'm not allowed to do this. And this problem would be much more difficult, and we'd have to solve it in a different way. All right, so then part B, what will be the volume of CO2 produced in this reaction? Well, I can actually use my same equation in my same sequence because it's the same discussion. So if I'm looking for CO2, I just have to finish my sequence. So from 0.35, representing my coefficient of 1, to my coefficient of 3, I need to triple that. And that becomes 1.05 liters. And so there's my answer to part B. 1.05 liters, of CO2 would be produced. And so that's as simple as it gets. That is kind of this shortcut with using Avogadro's law to use volumes in place of moles in a sequence to answer a stoichiometry problem. Now, I'll be honest, this is something that you're not going to see very often, but it is something that we can do if we know that the pressure and the temperature are constant during a reaction, and that's because